Hello everyone, this is Vasant, a ninepointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to discuss a new topic called shear stress and shear strain. So we discussed a lot on axial loading. In that we discussed about normal stress and normal strain, right? So shear stress and shear strain, these are consequences of shear load, right? So we already know about shear load, right? What is shear load? Shear load will act along the cross section of the member, right? So suppose if you take this block, so you are applying shear force B along the cross section, so it will create shear stress and it will create some deformations. That deformation can be expressed in terms of shear strain. So because of the shear stress, there will be change in shape. Suppose if you take any small element over here, so that shape here will now become something like this, right? So the shape of the element is changed. If you want to see macroscopically, see this is the rectangular box type of thing. So finally it became like this, right? So you can it is clearly visible over here. So there is change in shape, right? So this is what is the value of average shear stress? Average shear stress is given by V by A. Here it is V by A into D, right? So equality of shear stresses. See, if you go over here, you applied V like this, right? You applied V like this. Suppose if you apply tau, then what is the force acting over here? It is tau into AC, right? Suppose this is also of length A. This is cube. Suppose this is a cube of length A. Some all the values as A. So if you apply shear stress on one face of the element as tau, then what is the shear force on that element? The shear force will be shear stress into that area, that is A square, right? So if you are applying force like this, then there should be equal and opposite force such that it should be in equilibrium, because whatever shear stress is developed, that is in equilibrium only. So suppose it might be fixed to something, should be fixed to something. So because of that, equal and opposite shear force tau into A square will develop, right? Then what is shear stress on this face? That will be tau into A square divided by area of this face, right? Area of this face is A square, so that will be tau, right? Tau in this direction. So similarly, now we have shear stress tau like this, shear stress tau like this, right? So it will create equal and opposite forces at a distance d, means it is a couple. So to cancel that couple, there should be equal and opposite one more couple. So that is possible over these faces, right? If this is creating clockwise couple, we should have an anti-clockwise couple. So again, same magnitude wala tau shear stress will create on these two faces. So if you see on overall four faces, all the faces have the tau shear stress same, right? So in magnitude we can say it is same, but in terms of direction, we need to have some sign convention, right? So what should be that sign convention? That sign convention is a shear stress acting on a positive face. What is positive face? See, this is x. Then normal of the surface, which is along the positive axis direction, that is positive. Means, see, if you take this face, then outward normal of this face is in this direction, right? So that is along the positive x direction. So, and this is also a positive face, right? So positive face, for positive face, positive direction is the, for positive face, positive direction is the, if the shear stress is in positive direction, then it is positive. So positive face of an element, you see over here, of an element is positive if it acts in the positive direction of one of the coordinate axes, and it is negative if it acts in the negative direction of an axis. Suppose for negative phase, it is positive if it acts in the direction of negative coordinate axis, negative direction of any axis, and negative if it acts in a positive direction. So this is the sign convention for shear stress. So if you see over here, for this phase, this is y, this is x, this is z. So along x direction, the rightmost one will be the positive surface. So this is positive surface. So for positive surface, the shear stress is positive if it acts in any one of the positive direction of the axis, right? So here the shear stress curve is acting along positive y direction. So here it is positive, right? If you consider over here, the direction is like this, right? So this is negative surface, right? This is negative surface. So for negative surface, the shear stress is positive if it is in negative direction. The shear stress direction is in negative. So see, this is negative y direction, right? So again, the tau over here is positive. So similarly, these two are also positive. So that is why we said equality of shear stress in perpendicular planes, right? This one are perpendicular. This one are perpendicular. This one are perpendicular. This one are perpendicular, right? So this is how this is about sign convention of the shear stress and equality of shear stress. Let us move ahead. What about shear strain? We said that because of the shear load, there will be some deformations. That deformations will cause change in shape of the object. So then how will you calculate shear strain similar to that of we calculated normal strain? In normal strain, we calculated normal strain epsilon is equals to change in length divided by worsening length. But in this case, the change in dimensions is very less, so we neglect that in case of shear. In case of shear, there will be change in angle. So we need to have some sign convention for that angle, and we represent shear strain as that angle. Okay, so shear strain will be measured in angles, right? So it can be represented in degrees or it can be represented in radians. So we need to have some sign convention, right? So if you see the sign convention, you can take any sign convention, but we should follow strictly one sign convention. Shear strain in an element is positive when the angle between two faces or two negative faces is reduced. Okay, the strain is negative when the angle between two positive faces is increased, right? See, means this is another sign convention. This or wala combinedly give you another sign convention. So these two positive faces and this between two positive faces is increased. Okay, so see over here, this is something wrong over here. See, I will explain what it is. See, if you take any two perpendicular positive faces or negative faces. See, for this element, these are negative faces. This is negative. This is negative, right? So if you see over here, initially the body will be like this. Now the body become like this, right? So the initial angle between two perpendicular directions is pi by 2. After that, it is decreased in this direction by gamma by 2. In this direction, gamma by 2. So what is whole decrease in the angle? That is gamma by 2 plus gamma by 2, right? That is gamma, right? So gamma over here is shear strain. So that sign convention is as your wish. You can take positive or negative. You can take reduce in angle as positive. You can take, or otherwise you can take increase in the angle as positive. But see, we generally take for positive surfaces, if angle is decreased, then it is positive. But here, what these are negative surfaces. So for negative surfaces, the angle is decreasing. So it should be negative, right? So how much angle is decreasing? Gamma. So for this, according to our sign convention, it should be minus gamma, right? So you may say that means if you consider any two positive surfaces in this example, it should be increase in the angle. That is, you can see over here, this is pi by 2 minus gamma, right? So these are positive surfaces, right? These two are positive surfaces. So if you take these two perpendicular surfaces, the change in angle between these two surfaces is also a shear strain. So this is pi by 2 gamma. Opposite angle should be 180. So how much this should be? This should be pi by 2 plus gamma. So if you consider two positive surfaces, if the angle is increased, then it is negative. So gamma minus gamma is shear strain again. Understood? So this is about sign conventions of the shear strain and how we measure it. Let us move. Hooke's law on shear. We already discussed Hooke's law in tension and compression. In case of axial loading, we discussed Hooke's law in tension, compression, right? We wrote sigma normal stress is equals to E into normal strain epsilon, right? So this is E, this E is modulus of elasticity. Right. So similarly over here, tau shear stress should be is equals to some constant into gamma, that is shear strain. Right. So that constant is G over here. This is modulus of rigidity or shear modulus. We already know that E, G, K, mu, these are elastic properties, right? So out of these four, we now covered E and G. Okay. Actually, shear stress is a huge topic that we will cover in future lectures. But here we just given some basic idea about shear stress and shear strain to understand some few concepts which we usually thought before shear stress. Okay. So with this we end today's lecture. In next lecture we are going to deal with Poisson's ratio, that is this one, this mu. Sometimes we will also represent it with mu. So until then, take care. Bye bye from 9pointer. Thank you.